So let's finish up the final exam review, questions 27 through 38. Let me begin with question 27 and get over to here. So these, I would imagine you can enter into your calculator. That's all I'm asking you to do here. So let me concentrate on multiplication. I labeled this C11, C12, C13. The dimensions of the matrix that you're going to get when you multiply a 2 by 2 times a 2 by 3, well, the inner indices match. So the outer indices, you're going to get matrix C is going to be a 2 by 3 matrix. So, okay, this is C11, first row, first column, first row, second column, first row, third column, and so on. Second row, first column. You get the products elements in this matrix by multiplying this row by this column. This row from A times this column from B. So first row of A times first column of B, first row of A times second column of B, and then first row of A times third column of B. Then you move down to the second row of A times the first column of B, and so on. And I'll let you do the arithmetic there. Problem 28 is simply that the inner indices don't match. And if they don't match, you can't multiply them. That's it. So it's kind of strange. Sometimes you can multiply things in one direction, but not in the other. But that's just the nature of matrices. Matrix multiplication is not commutative. That is, the order makes a difference. Let's look at example 29. If you're going to give me an augmented matrix, then it should be a 4 by 5 matrix, and this should be in here. But that's not what I'm asking for. I'm asking for a system of equations. So this is your A, this is your B, this is X. You calculate that as X is A inverse times B. Now for a 4 by 4, I certainly don't expect you to do that in your head. Let's do it on the graphing calculator since you're not going to be able to do Desmos test mode with matrices on the exam. They just don't do matrices in test mode, at least as far as I know. I've already got the matrices entered. Let's just type them out. Here's matrix A. Here's matrix B. We want A inverse times B. It's not a bad idea to double check your matrices by printing them out like this. So here's A. Click the X inverse key and then multiply that by matrix B. You don't need the time symbol there. It understands that they're multiplied. And bam, there you go. That's your solution. 8 for X, -4 for Y, 9 for Z, and 3 for W. So nice. All done with that one. There we go. Let's keep going. Solve a problem by Cramer's rule. You know, it'd be nice if you knew how to calculate a 3 by 3 determinant by hand. I'm not going to go over that here. I will go over how to get DZ, for instance. And you're going to take the right-hand side here and replace the coefficients of Z by those coefficients. So the rest of the coefficients are already in place. I just got to put in -1, 1, and 17. As far as calculating the determinant of that goes, let's again do that on our graphing calculator. So matrix C should already be in there. Let's take a quick look. Looking good. Now I want the determinant of that matrix. So go to the matrix menu, second X inverse, go over to math. The first operation there is what we want. You have to tell it you want the determinant of matrix C. So back to the matrix menu again. This time we want the determinant of matrix C. And bam, -71. That doesn't look right. Let me just double check. -2, 1. Oh, that should be a 0 there. So let me go back and fix that. Go over to edit first, then down to matrix. We've got a 3 by 3. That should be a 0. Let's do that again. If you hit the second key, then the enter key, it'll bring up a previous calculation. That looks a little bit better. Negative 57. Let's plug that in and finish this up with Kramer's rule. So x is dx over d, which in our case would be negative 38 over negative 19, which is 2. dy over d is negative 19 over negative 19, which gives me a 1. And finally, dz is negative 57 over negative 19, which gives me a 3. So the solution in the XYZ form is 2, 1, 3. Please don't make me go digging around to figure out what is what. Just put it right up here for me, please. Partial fraction decomposition. This is a good one. Let's take a look here. You're going to put a term in the numerator like this for every binomial term in the denominator. This is not a repeated linear factors case. I don't have a squared or a cube, so I don't need to do any repeats here. The trick here is to multiply both sides of this equation by the LCD. And our LCD is x plus 2 times x minus 5. X minus 5. If I multiply this by the LCD, the denominator is going to cancel with that. So you're just left with the numerator. Here, x plus 2 is going to cancel out of that. It's going to leave me with a times x minus 5 and b times x plus 2 once that cancels. There's a couple ways you could solve this. The fastest way I would suggest is by picking values of x that make your equation simple. So if I set x equal to 5, for instance, then I get 7 times 5 is 35. So 35 minus 14 is 21 equals a times 0 plus b times 5 plus 2 is 7. Essentially 7b equals 21, meaning b is 3. Nice. We need to figure out what a is. This time I'm going to set x equal to negative 2. And that's going to give me 7 times negative 2 is negative 14. Minus 14 again gives me negative 28 equals a times negative 2 minus 5 is negative 7. So 4 equals a. Let's put those in here and write our solution in a nice, neat form that your instructor would appreciate. That's going to be 4 over a plus 2. 4 over a plus 2, or excuse me, x plus 2, plus 3 over x minus 5. And that is your partial fraction decomposition. Okay. Down here, we've got to figure out what inequalities were used where and how. Let's start with the circle, which is here. The circle is not shaded. So this has to test false in order for us to shade outside the circle. Now, in order to test false, well, 0 squared plus 0 squared, well, what would make that test false? Is that going to be a greater than or a less than? Has to be a greater than or a less than because we've got a dashed line here. In this case, it would test out false if you had 0 is greater than 4. So the greater than here, x squared plus y squared is greater than 4. How about for the second one, the parabola? Well, it's going to have to be a less than or equal to or greater than or equal to because this is a nice smooth line. And then what? We want that to test true because it's shaded on the inside. So if I test 0, 0, I have 0 and 0 minus 4 is negative 4. Which one of these is going to make that true? That would be a greater than or equal to. So the other part of this is x is greater than or equal to y squared minus 1. And that does it for the system of nonlinear inequalities. Beautiful. Let's keep rolling. Problem number 37. Actually, you know what? How about if I do this one? Let's go in order first. Sticking with inequalities, here's another system of inequalities. We got to graph these by plotting some points first. So if I plug in to this inequality, if I graph the equation, plug in an x equals 0, I get y equals 4. If I plug in a y equals 0, I get x is 3. That's these 2 points here. I'll draw a solid line between those. Then down here for the next one, if I let x equals 0, negative 12 equals 2y, so negative 6. Down here for y, if I set y equal to 0, 12 moves to the other side, I get 4 for x. This one I'm going to draw with a dashed line because of the sign of the inequality. It's just a greater than. Now I get to test points. 0, 0 is my favorite test point. Let's test that in here first. Is 4 times 0 plus 3 times 0, is that less than or equal to 12? Yeah, that's true. So I'm testing that in the red line. That means I would shade below here like that. What about this one? If I did 0, 0 as a test point again, nothing wrong with that. Then let's see. 3 times 0 minus 12, is that greater than or equal to 0? Well, negative 12 greater than 0? I don't think so. So that test false. So we got to shade the other side of this line. That would be down here. These shaded regions overlap in this little piece of wedge down here. So that would be your solution. You could shade everything and then just circle where they overlap. That's fine as well. But either way, I want you to clearly mark your solution. This is our solution right down in there. Moving forward, system of nonlinear equations. You know, this is one for which you might want to graph this on Desmos. And I think I've got that done for us here. So let me take a look. There we go. It takes a little bit of finesse to see that there's 4 solutions. You're gonna have to kind of zoom in and stretch a little bit to see that. But there are 4 solutions. They're not nice, neat integers, at least not all of it. So keep in mind that there are 4 solutions. So let's find them. I would start by adding these 2 equations together. 1 and 3 gives me 4x squared. The y squares cancel out. Minus 36 equals 0. Do I have that equation plugged in right here? Yeah, okay. So let's see. Why doesn't that look right? Okay, so I had the wrong sign here. So the solutions do work out to be nice, neat, even integers. That's great. I'm still going to want to see the work, and chances are when you do this, you'll end up with a square root, at least for one of the solutions. So do take care to understand what we're doing here. Let's continue. If you add these down, the y squared cancels out, move the 36 to the other side, and then divide by 4. X squared equals 9, x equals plus or minus 3. Now, if I set x equal 3 in one of these equations, I would get 3 squared minus y squared plus 16 equals 0. So I'll move the y squared to the other side. Now I have 9 plus 16, that's 25. So plus or minus 5 equals y. If I did the same thing with 3, it's going to be negative 3, I'd end up with the same thing. Plus or minus 5 equals y. So that means when x is 3, y could be 5, or y could be negative 5. When x is negative 3, y could again be 5, or y could again be -5. So that's all 4 of your solutions. Kind of a quick hitter for problem number 35. You have points at 2, 0, and 0 and 4. That's really all I need here. I've given you the other points as well. But the center is at 0 and 0, so it's going to be x squared over a squared plus y squared over b squared equals 1. A is this distance right here, so it's x squared over 2 squared plus y squared over 4 squared equals 1. Beautiful. Now these 4 points are useful. Those are the vertices of your ellipse. How do you know it's an ellipse versus a hyperbola? If you're looking at this, that's right. This should have a minus if this was a hyperbola, like this one. Problem number 37. So let me kind of zoom out a little bit here, make our screen bigger. Again, you can do this on Desmos, but Desmos isn't going to give you everything that you need. So after you divide everything by 16 to get a 1 on the right-hand side, 4 and the 16 cancel, leave you the 4, nothing cancels there, I've got a 16. I'll write those terms as squared. The center is going to be -2, +3. It's going to open in the x direction because that's the positive term that I have here. Start out with the center, -2 and 3. Go to the right 2, to the left 2, put some points there, and go up 4 and down 4, and put some points there as well. Let's play connect the dots through these points. I give a couple points for drawing this box correctly, and then the diagonals of the box should go directly through the center. Here and here. Like that. This opens left and right. So let's draw a hyperbola that opens left and right, and then we're done. Now, the hyperbola has asymptotes of these diagonal lines, which is why I want to see them. Comes close to, but never quite touches those diagonal lines. And yeah, hope I don't give you the spins real quick here, but there we go. It's okay if you accidentally touch it a little bit. Just don't ricochet off and start curving out. All right, this is going to get closer and closer here. Sequences. There's a couple problems that I left out that you'll see on the exam. And there's also a little bit of a typo here. If you divide this term by this term, you reduce it and you get a common ratio of -1/4. That term doesn't fit here as well. So I think that one should really be, that should probably be an 8. Now, if we multiply by -1/4, that would be a 4. And then multiply by -1/4 again. And next term in this sequence, in order for it to be a geometric sequence, should be -1. So a little bit of a typo here on my part, my bad. That's meant to be a geometric sequence. The 5th term of this new sequence would be -1/4 times that would be +1/4. D or R, in this case, it'd be R equals this common ratio, which is -1/4. You should also be able to give me A sub n, general form of the terms in this sequence. So I've got that stuff here in blue for arithmetic sequences and in red for geometric sequences. So in terms of geometric sequences, it's going to be 64 times -1/4 to the n minus 1. Last but not least, I could ask you for something like S sub 7, sum of the first 7 terms. I don't want you to add up terms like this. I'll keep it small. Your part is to use this formula here. That's going to be 64 times 1 minus negative 1/4 to the 7th power over 1 minus negative 1/4. That can be kind of a pain to plug into your calculator. So let me help you out with that a little bit. Let's go over to our graphing calculator and clear this stuff out. Clear that, yes. 64 parentheses 1 minus, you know what, actually, you know what? Let's do this first. Let's take negative 1 divided by 4 and store it in X. So there you go. Store that there. It's just going to make it easier to plug in my expression. I'll do 64 parentheses 1 minus X raised to the 7th power. That'll give me, when I finish filling this out, give me the sum of the first 7 terms over 1 minus X. But typically, I'll want that answer as a fraction. So you can hit the math key and then press enter twice. And there you go. 3277 divided by 64. Nice. 3277 over 64. Okay. How about the next one? Let's take a look at that. That's an arithmetic sequence. I don't think I screwed this one up. The next term, a sub 5, would be 56. And that's going to mean that D is negative 4. That's your common difference. D equals negative 4. The general term in this sequence is going to follow this pattern. So it's going to be a sub n equals 72 plus n minus 1 times negative 4. You could simplify this if you want to distribute and whatever. I'm happy with it like that. If you want the sum of the first 7 terms, again, it's easy to add those up just by writing out the few next terms. But humor me and use the formula. So it's going to be S sub n is going to be a sub 1 plus a sub n. Well, I don't have what a sub 7 is. Not that it's hard to get. So I'll use this one. It's going to be 7 over 2 times 72 plus 7 minus 1 times negative 4. So 7 over 2, that term out in front, let's just call that 3.5. 3.5 parentheses 2 times 72, well, that's 144 plus 7 minus 1, that's 6. 6 times negative 4 is negative 24. And if this gives me something that's not an integer, that has a decimal, then there's something wrong. I think we're okay here. 420. Beautiful. Last but not least, last but not least, problem number 36. I'm sorry, I'm a little bit out of order here. Again, kind of a typo here. Well, not exactly a typo, but it was harder than I wanted the way it's written. Here's your parabola. It has a vertex at negative 4. If that's negative 4, all that disappears and you're left with negative 32. So that's your vertex. It's not going to fit on this graph. Sorry, we'll graph it on Desmos. The other thing we're going to need from this is what P is. Remember, you're going to have to try and find P to find, first of all, your focus, then your directrix. P is 1 over 4A. That's A. A equals 1 over 16. So 1 over 4 times 1 over 16, that's going to be 1 divided by 1/4, which is 4. So this parabola has to open up, which means your vertex is going to lie 4 to the north. Your directrix is going to lie 4 to the south. Let's see what those look like. Let's shut these off and graph this one. Notice nothing's fitting on this yet. So we'll zoom out a little bit. If you look at your vertex right here, going 4 up from that means you're going to add 4 to the y coordinate. So adding 4 to the y coordinate puts you right there at -4 and -28. If you go down 4 from here, that puts you at the horizontal line, y equals -36. Beautiful. To find the y-intercept, you could set x equal to 0. Okay, and you get -31. That's fine. If you set y equal to 0, you get these two monsters. Now, if I ask you, you should be able to show me the calculation of the x-intercepts. That's down here. You get the x-intercepts by setting y equal to 0. If you set y equal to 0, I can move the 32 to the other side and then multiply both sides by 16. 16 times that gives me 512. The 16 cancels this out here. That's still squared. Take the square root on both sides, move the 4 to the other side. That's going to give you -4 plus or minus the square root of 512. Don't ask me why, but I know that 512 is 256 times 2. So I get -4 plus 16 times the square root of 2, and -4 minus 16 times the square root of 2. Those numbers are right here and here. And that does it. Good luck on the exam. And if you stuck with me all this way, then right, I made it to the end. Next to your name, and maybe I'll give you a couple extra credit points. Good luck.